welcome to the next lesson, and let's continue where I left off. So we are now we are talking about the meaning of independence, and so the next thing is theorem 3.5. Okay, so theorem 3.5: if events A and B have non-zero probabilities, then they are independent. If and only if. IFF stands for if and only if. The probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. Okay, if and only if means logically equivalent. So what theorem 3.5 says is if events A and B have non-zero probabilities, then they are independent, meaning events A and B are independent if and only if those two equations hold. And so the proof of theorem 3.5 is as follows. So first let's prove the forward direction of the proof. So this is an if and only if statement saying these two statements are logically equivalent. That means one way to prove an if and only if statement is to show that if this is true, then that's true, and also that if this is true, then that's true. So the forward direction is we're going to assume that A and B are independent and show these two equations hold with that assumption. Okay, so if A and B are independent, then the probability of A given B is equal to the probability of AB over the probability of B. And so that implies, right, so A and B are independent. Then the probability of A given B is equal to the probability of AB over the probability of B. That implies that the probability of AB is equal to the probability of A given B times the probability of B. And that the probability of AB is equal to the probability of A times the probability of B, right? And so this equation is because A and B are independent. Since because A and B are independent, the probability of AB is equal to the probability of A times the probability of B. So what that implies is that the probability of AB is this, and so that means that this product is equal to that. So that implies that the probability of A times the probability of B is equal to the probability of A given B times the probability of B. Okay, so that implies that, well, here's the probability of B on both sides. If I divide both sides by the probability of B, then that means that the probability of A is equal to the probability of A given B. Okay, so the probability of A is equal to the probability of A given B. That's this equation. So we showed that one. And then I guess I'll write this over here. The probability of B given A, this is very similar to that proof, is equal to the probability of BA over the probability of B over the probability of A. And that implies that the probability of BA is equal to the probability of B given A times the probability of A. And so also the probability of BA is equal to the probability of B times the probability of A, because again, A and B are independent, and so that means that that equation holds. And so that implies that since probability of BA is equal to this and that, they're equal to each other. So the probability of B times the probability of A is equal to the probability of B given A times the probability of A. And that implies that the probability of A is equal to the probability of B given A. Okay? Probability of B is canceled. Probability of A is canceled, so the probability of B is equal to the probability of B given A. Okay, and so we showed, assuming that A and B are independent, we then show that that implies that these two equations hold, this equation and that equation. Okay, so the forward direction of the proof is done. Okay, so now let's prove the backwards direction of the proof. Okay. Okay, so on the other hand, so this is now going to prove the opposite direction. This will prove that assuming these two equations hold, then A and B are independent events. Okay, so if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B, then, so if those two equations hold, then probability of A is equal to the probability of A given B. And that equals to the probability of AB over the probability of B. And that implies that the probability of AB is equal to the probability of A given B times the probability of B. Okay, so we're starting with this assumption here, that the probability of A given B equals the probability of A. And so this is equal to the probability of A given probability of B by the definition of conditional probability. And that implies that probability of AB is equal to probability of B times the probability of A given B. Oh, sorry. That means that this is equal to this times that. So it's the probability of A times the probability of B. And so that implies that A and B are independent. Okay, so if these two equations hold, then A and B are independent. And so actually we only need one of them. So with just this one equation, we showed the other one's true also. Okay, and so that is the end of the proof, if and only if statement. We broke both directions of the if and only if statement, and the proof is done. Okay, so let's keep going. Okay, so consequences of that theorem. So consequences of theorem 3.5, that last theorem, and the definition of independence. Okay, so A, consequence A, is if events A and B are independent, then events A prime and B prime are independent. Okay. Okay. Also B, another consequence is that events A, if events A and B, if A and B as events have non-zero probabilities. If A and B have non-zero probability less than 1, then they are independent. If and only if the probability of A given B prime is equal to the probability of A, and the probability of B given A prime is equal to the probability of B. So consequences of theorem 3.5 and definition of independence. If events A and B are independent, then A prime and B prime are independent. If A and B have non-zero probability less than 1, then they're independent if and only if those two equations hold. Okay, and so those are consequences of the last theorem, theorem 3.5, and the definition of independence. Okay, give you a second to look at it. Okay, let's keep going. So example 3.12. Examples of independent events. Okay, so examples of independent events. A, show in two coin tosses, or fair coin. If A is the event of heads on the first toss, and B is the event of tails on the second toss, then A and B are independent. Okay, so part A, show in two coin tosses if A is the event heads in the first toss and B is the tails on the second toss, then A and B are independent. Okay, so when you have a coin, right, there's two possibilities for the coin flip. There's heads or there's tails, right? So H represents heads and T represents tails. Okay. And so the sample space of this experiment is either heads, 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 tails, tails, heads, or tails, tails. Right? Those are the four possibilities when you flip two coins, heads or tails each time. So that's the sample space. So the probability of A, the probability of heads on the first toss is the number of elements in the sample space where heads are in the first toss divided by the total number of simple outcomes in the sample space. So n is 4, and the numerator and sub A is the number of the sample points where heads is on the first toss. So that's 1, 2. So there's 2 of them like that. That's 1/2. The probability of B, the probability of tails in the second toss, is the number of simple outcomes in the event B divided by the total number of simple outcomes in the sample space. And sub B is, well, the tails in the second toss. So that's 1, 2. There's 2 of them like that out of the total 4. And so the probability of B is also 1/2. The probability of A and B would be the number of sample points in the event AB divided by the total number of sample points. So the total number of sample points is 4. Now AB would be heads on the first toss and tails on the second toss. And so there's only 1 like that. So it's 1 out of 4. So the probability of AB is equal to the probability of A times the probability of B. And that's because the probability of AB is 1/4, the probability of A is 1/2, the probability of B is 1/2. So 1/4 equals 1/2 times 1/2. And so the probability of AB equals probability of A times probability. That's true. And so that means that A and B are independent. And so because that equation is true, that implies that A and B are independent events. Okay, so A and B are independent events, and that shows A and B are independent events. Okay. Keep going. So now this. Okay. Okay, next, example 3.13. Okay, example 3.13. Okay, so here an experiment is measured in only success or failure. Okay, so this is an important type of experiment, one in which the outcomes are only success or failure. Okay, so suppose little p is the probability of success. And q, which equals 1 minus p, is the probability of failure. If the experiment is repeated 4 times under identical conditions, what are the probabilities of obtaining zero successes, exactly 1 success, exactly 2, exactly 3 successes still, and exactly 4 successes. Okay, so example 3.13. An experiment is measured in only success or failure. Suppose little p is the probability of success, and q equals 1 minus p is the probability of failure. If the experiment is repeated 4 times, what are the probabilities of obtaining 0 successes, exactly 1 success, exactly 2 successes, exactly 3 successes, and exactly 4 successes? Okay, so here's the solution. I'm going to let S1, S2, S3, S4 be events of successes on the first, second, third, fourth performance of the experiment, respectively. So let S1 to S4 be events of successes on the first, second, third, fourth performances of the experiment, respectively. So that means that S1 is the event of success on the first performance of the experiment, S2 is the event of success in the second performance of the experiment, S3 and S4, so on. Okay, and let F1, F2, F3, F4 be events of failures. On the first, second, third, fourth performances of experiments. Okay, so S1 and S4 are successes in the first to fourth performances of the experiment, and F1 to F4 are the events of failures on the first to fourth performances of the experiment. Okay, so using independence of events, we get that the probability of 0 successes is equal to the probability of failure in the first performance, failure of the second, failure in the third, and failure in the fourth. That would be the probability of the intersection of event F1 and F2 and F3 and F4. Right, because F1 to F4 are failures in the first to fourth performances of the experiment. And so the probability of the intersection of all 4 of those F's would be the probability of failure in all 4 performances of the experiment, which means there would be 0 successes. So the probability of the intersection of those is the probability of F1 times the probability of F2 times the probability of F3 times the probability of F4. And that's because F1 through F4 are independent events. You can check the equation. The probability of F1, F2 is equal to the probability of F1 times the probability of F2. Okay? And so this is the probability of failure of each of the 4 performances of the experiment. Each of them have probability Q. Q is the probability of failure in any performance of the experiment. So this is Q times Q times Q times Q. That's Q to the 4th power. And so the probability of 0 successes is Q to the 4th power, where Q is the probability of failure in any one of the 4 performances of the experiment. Okay, so that's the probability of 0 successes. And so we're done with 0 successes. Okay? So let's do the next one. So I'm going to let S1, S4, and F1 to F4 be the way I define them here. And I'm just going to erase this though so I have more room to work. So those are the events of success and failure, the 4 performances of the experiment. Okay? Right? It's either success or failure each time, right? So the probability of 1 success, that means you perform the experiment 4 times, and exactly 1 of the 4 times you succeed, the other 3 times you fail. So this is the probability where you succeed in the first time, fail in the second one, fail in the third, and fail in the fourth. That's plus the probability of failing in the first one, succeeding in the second one, failing in the third one, and failing in the fourth one. This is plus the probability of, so it would be the probability of the union of these mutually exclusive events, and then it would be the sum of their probabilities. This is plus the probability of failure in the first one, failure in the second one, success in the third one, and failure in the fourth one. Plus the probability of failure in the first, failure in the second, failure in the third, and success in the fourth. Okay, so either you succeed in the first, fail the rest, succeed in the second, fail in the rest, succeed in the third, fail in the rest, succeed in the fourth, fail in the rest. And so you just find these probabilities, and so for each probability, right, this would be the probability of succeeding 1 time and failing 3 times. So this would be the probability, so let me write something here. The probability of S1, F2, F3, F4, that would equal to the probability of S1 times the probability of F2 times the probability of F3 times the probability of F4. And so you see how I can break that up into a product of 4 probabilities. The probability of success is P, and the probability of failure is Q. And so that would be P times Q times Q times Q. That would be P times Q cubed, because you succeed once and fail 3 times. And you could do the same thing for the other 3. So the probability of this is P times Q cubed, right? The probability of this is also P times Q cubed, because you succeed once and fail 3 times by similar reasoning to that. And then plus the probability of that is succeeding once, failing 3 times, plus the succeeding once, failing 3 times. So it's PQ cubed plus PQ cubed plus PQ cubed plus PQ cubed. And that's equal to 4PQ cubed. So 4PQ cubed is the probability of 1 success. And so now we found the probability of exactly 1 success. It's 4PQ cubed. Okay, it's a little hard to say. Okay, that's the probability of exactly 1 success in this type of experiment. Okay, so now let's look at the probability of 2 successes. Okay, so the probability of exactly two successes would be the probability of succeeding in the first and second ones and failing in the third and fourth, plus the probability of succeeding in the first, failing in the second, succeeding in the third, failing in the fourth, plus the probability of succeeding in the first, failing in the second, failing in the third, and succeeding in the fourth, plus the probability of failing in the first, succeeding in the second, succeeding in the third, failing in the fourth, plus the probability of failing in the first, succeeding in the second, failing in the third, then succeeding in the fourth, plus the probability of failing in the first, failing in the second, succeeding in the third, and succeeding in the fourth. Okay, so those are all the ways you can succeed 2 times and fail 2 times, and thus fail 2 times out of 4 performances of the experiment. First and second, first and third, first and fourth, second and third, second and fourth, and third and fourth. Okay, and so each time you succeed twice and fail twice. So this would be, and there's 1, 2, 3, 4, 5, 6 of them. So this would be 6p squared q squared. Each one would be q squared, p squared, q squared. And there's 6 of them. So that's 6p squared q squared. That's the probability of 2 successes. And so the probability of exactly 2 successes is 6p squared q squared. Okay. Right. So here, the in-between step is that the probability of 2 successes is the probability of this union that, union that, union that, union that, and union that. And then that's equal to the sum of the probabilities of those mutually exclusive events. These 6 events are all mutually exclusive. So you can use axiom 3 to say that the probability of a union of mutually exclusive events is the sum of their probabilities. Okay. Okay, so let's go to the next one. So the next one is the probability of 3 successes. So the probability of exactly 3 successes. That's the probability where you succeed in the first one, succeed in the second one, succeed in the third one, and fail in the fourth one. Plus the probability of succeeding in the first, succeeding in the second, failing in the third, and succeeding in the fourth. Plus the probability of succeeding in the first, failing in the second, succeeding at the third, and succeeding in the fourth. Plus the probability of failing in the first, succeeding in the second, succeeding in the third, and succeeding in the fourth. So you fail the fourth, third, second, first. That's all the ways of exactly 3 successes. Each one is failing once and succeeding 3 times. And so that would be p cubed times q to the first, which is q. P cubed q is each of them. 3 successes, 1 failure. And there's 4 of them. And so it would be 4 p cubed q. So the probability of 3 successes is 4 p cubed q. And so that's the probability of exactly 3 successes. Okay. Makes sense? And I'm leaving out the in-between step where the probability of 3 successes is the probability of the union of these 4 mutually exclusive events, which is then equal to this is the sum of the probabilities of those 4 mutually exclusive events by axiom 3. Okay? But each one of these is p cubed q, and there's 4 of them, so it's 4 p cubed q when you add them up. Okay, so next is the probability of 4 successes. So the probability of 4 successes, that's the probability of success in the first, success in the second, success in the third, and success in the fourth. And so the probability of 4 successes is the probability of succeeding all 4. And so that's just equal to p to the 4th. And there's only 1 of them. Okay, so the probability of 4 successes is p to the 4th. Okay, so exactly 4 successes. And so now we found all 5 of those probabilities. Okay, and so that's the solution to example 3.13. Okay, so 3.4 is additional applications and examples. So 3.4 is additional applications and examples. So here's the example. A player wins with 3 points, and you win 1 point per game. Okay, so you play a game. If you win, you get a point. If you lose, you win. Suppose player 1 has player A has 1 point, and player B has 2 points. Then probably that A wins, given that B already has 2 points. Okay, so this is just a fun example. A player wins with 3 points, and you win 1 point per game. So you play one game at a time until there's a winner. Someone has 3 points. So suppose player A has 1 point, and player B has 2 points. Then the probability that A wins, given that B already has 2 points, what is that, right? What is the probability of that? Well, A needs 3 points to win, and B already has 2 points. So B wins just one more game. B will have 3 points and win. So A has to just win every time in order to win the whole thing, right? Player A starts with 1 point, okay? And so, in order to get 3 points, player A has to win 2 more times. And so, this is the probability that A wins the next two plays, right? And so that's equal to the probability that A wins the next game, next play, times the probability that A wins the play after, next. Okay, and so there's a 50-50 chance of each winning. So the probability that A wins the next play is 1/2 times the probability that A wins the one after that. So 1/2 times 1/2 is 1/4. So the probability that A wins, given B already has 2 points, where A is 1 point, that's 1/4. Probably that A wins the next two. 1/2 times 1/2. And so the probability that B wins, given that B already has 2 points, right? So what's the probability B wins, given that B already has 2 points? And so that's equal to 1 minus the complement of that. The complement of B winning, given B already has 2 points, is the probability that A wins, given B already has 2 points. And we already found that probability. The probability that A wins given B has 2 points is 1/4. So this is 1 minus 1/4. That's equal to 3/4. Okay, and so we've now found both probabilities. Okay, so the stakes in this situation, the original situation, is that one out of every 4 times A will win in this situation. And so that means the odds are staked 3-1 in B's favor. Okay, so the probability of A winning in this case is 1 out of 4, and so B is 3 times more likely to win than A. For every 1 time A wins, B wins 3 times. So B is 3 times as likely in this scenario to win than A. Okay. Okay, so that's that. And so let's continue to the next one. Okay, so 3.5 tree diagrams. Okay, so 3.5 tree diagrams. Example 3.17. Okay, so this is a long example. Okay, I'm just gonna write it out. Samples arriving. So samples at a lab. I'm gonna abbreviate this a little bit. So samples at a lab are given tests to find chemical X. Okay, so technically it's test to find traces of chemical X, right? So it's looking for chemical X in substances. So samples at a lab are given tests to find chemical X. If test A is positive, then the sample goes to test B. If test B is positive, go to test C. If test C is positive, the sample contains chemical X. Suppose the probability of false positive for tests. So suppose the probability for a false positive for test A, B, C are 0.05, 0.10, and 0.15, respectively. And the probability for false negatives are 0.01, 0.02, and 0.03, respectively. Suppose 10% of samples that arrive at the lab contain chemical X. Most 10% of samples at the lab contain chemical X. Okay, so part A, draw a tree diagram. Okay, so let me just go over the example again. 3.5 is tree diagram. So example 3.17, samples at a lab were given tests to find a chemical called chemical X. If test A, the first test, is positive, then the sample goes to test B. And if it's not positive, it doesn't go to the next test. If test B is positive, it goes to test C. If test C is positive, the sample contains chemical X by these tests. Maybe that's the conclusion. Suppose the probability for a false positive for test A, B, C are 0.05, 0.10, and 0.15 respectively. And the probability for a false negative are 0.01, 0.02, and 0.03 respectively. Suppose 10% of the samples contain chemical X. And so draw a tree diagram for this situation. Right? And so these tests are not foolproof, they're not 100% accurate. And so it's possible that if the test comes back positive, that it's wrong. That it's wrong to say that it's positive, and so these are the probabilities that for each test, when it's positive, it's wrong. And a false negative would mean that the test comes back and says, no, your sample does not have chemical X, but it's wrong to say it doesn't because it does. And so these are the respective probabilities for tests A, B, and C to be wrong to say that chemical X is not in the sample, because it is. Okay? So let's draw a tree diagram to explain this situation. Okay? So you have your sample. You have your original sample. And so there's two possibilities. And so I'm going to illustrate those two possibilities by the symbol x plus and the symbol x minus. What x plus means is that your sample does have chemical X in it. And x minus is if your sample does not have chemical X in it. And so on these branches on the tree diagram, it includes the probability that the probability of that happening. So if you have a sample, there's a 10% chance. It says suppose 10% of the samples contain chemical X. So this is a 0.10 probability of happening. That if you have a sample, it does have chemical X. That means there's a 0.9 probability, 0.90 probability that if you have a sample, it does not contain chemical X. Okay, that's a 0.90. Okay, so the next thing that happens is when you take your sample, it either does or doesn't have chemical X. So let's say it does have chemical X. The first thing you do is you pass it to test A. And when you pass it to test A, either test A comes back positive or negative. Right? The chance of test A coming back positive, right? So test A, we have to work backwards a little bit here. Test A, first off, chemical X is in this sample. You went in this direction. So chemical X is in your sample. And so if test A comes back negative, if test A tells you it's not, chemical X is not there, there is a chance of that because test A is not foolproof. There's a possibility that it's wrong, that's a false negative. So the probability of a false negative is 0.01. And so there's a 0.01 chance that this branch happens, that you take a sample, it does have chemical X, and test A says there is no chemical X, that would make it a false negative. Test A is only right if it says chemical X is there because we're assuming chemical X is in that sample. And so saying it isn't is a false negative, and so there's a 0.01 chance of that happening. So otherwise, it would come back positive, which it should, and so that would be a 0.99 chance of happening. That would be 99% chance that test A would tell you correctly that chemical X is in that sample. Okay, now if it comes back negative, you stop. You don't, once a test comes back negative, you don't perform another test on it. So when test A comes back positive, you then perform another test. You perform the next test, test B on it. And so when you perform test B on it, what should happen is that it should come up positive, right? You'd want it to come back positive because its chemical X is still in your sample. So a false negative would be a 0.1 chance. A false negative would be a 0.02 chance. So there's a 2% chance that test B would be wrong and say it's not there. That means there's a 98% chance, 0.98 chance of test B coming back positive. So if test B comes back negative, you stop. If test B comes back positive, you then perform test C. And so there's still there's two possibilities. Test C comes back positive or negative. Chemical X is still in your sample here. We're still thinking that. So it would be false if it said it wasn't. So there's a 0.03 probability that test C comes back negative when chemical X is in your sample. And so there's a 0.97 chance, a 97% chance that test C is correct in saying that chemical X is there. And so now this is half of the tree diagram, and I labeled the probabilities there. So now the other possibility is that your sample does not have chemical X in it. That's a 90% chance, a 0.9 chance of happening. So you perform test A on it, so A plus and A minus. So either test A comes back positive or negative. Now, chemical X is not in your sample, and so it would be wrong to say it is in the sample. So now we're going to look at false positives. So a false positive for test A is 0.05. So there's a 0.05. The probability of A coming back positive being a false positive is 0.05. That's a 5% chance. So there's a 0.95 chance, a 95% chance that A comes back negative and correctly says that chemical X is not in your sample because it's not there. Okay, so if test A comes back negative, you stop, right? And so you only continue if the test comes back positive. So if the test A comes back positive, you perform the next test, which is B plus or B minus. That would mean that test B comes back positive or negative. Chemical X is not in your sample, So saying that it is would be a false positive, and so the probability for a false positive is 0.10. So this probability is 0.90. And so the test stops here at B minus. It keeps going for B plus. Then you have C plus or C minus. Okay. And so again, C plus would be a false positive, and that would be a 0.15% chance of happening. 15% chance. There would be a 0.85 chance, 85% chance of C coming back negative correctly, saying chemical X is not in your sample. Okay, so this is the tree diagram. Part A of example 3.17 is the tree diagram labeled with the probabilities to show all the possible scenarios of this experiment, of this situation. Okay. Okay, so I drew all the information from the problem on this tree diagram, and so I need this room. So I'm going to erase this now. And now I'm going to rely on the tree diagram to answer the rest of the questions. So I won't need any information from the original problem anymore. Everything I need to know is illustrated in the tree diagram. Okay. Just gotta erase this without erasing anything. Okay. Okay. So I'm just gonna erase that. Okay. There's the tree diagram. So part B is find the probability the lab falsely assumes presence of chemical X in the sample. Okay, so find the probability the lab falsely assumes presence of chemical X in the sample. So that means chemical X is not in the sample, and one of the test says it is in the sample. Okay, so the probability that the lab falsely assumes presence of chemical X, that is equal to the probability that test A comes back positive, test B comes back positive, and test C comes back positive, because in order for the lab to believe that chemical X is in its sample, the lab technicians see that all three tests come back positive, A, B, and C. So this is probably of A positive, B plus, and C plus, given the event X minus, which is when chemical X is not in the sample, right? So in order for the lab to falsely assume presence of chemical X, not only does all three tests have to come back positive, but it has to be in a situation where chemical X is not in the sample, right? So in order to be falsely assuming the presence of chemical X has to not be in the sample. So we want to find the probability of A plus, B plus, C plus given X minus. Okay, and so what is that? This is the probability of A plus, B plus, C plus, X minus over the probability of X minus. Okay, and so what is that? Then that's equal to so that's equal to the probability of A plus given X minus. So this is the probability of A plus given X minus times the probability of B plus given A plus X minus times the probability of C plus given A plus B plus X minus. Okay, and so then the probability of A plus given X minus is equal to is given x minus, what is the probability the test comes back positive? 0.05 times the probability of b plus given a plus and x minus, that's 0.10, and then times the probability c plus given a and b came back positive and x came back negative, that's 0.15. Okay, so it's just a product. So the probability that these three things come back positive given that this came back negative, that chemical x is not in the sample, is this times that times that. So it's 0.05 times 0.10 times 0.15. And so that's the same as so 75.00075. Okay. So that's the probability the lab falsely assumes presence of chemical X. Right? That's if given that chemical X is not in the sample, that all three of these tests come back positive. So it's this times that, which is that. Okay, and so that's part B. Okay, so let's do the next one. Okay, D, what percent of samples tested by lab or reported to contain chemical X? So what percent of samples tested by lab are reported to contain chemical X? So that probability of lab of reports chemical X in sample. So the probability the lab reports chemical X in the sample is equal to the probability that A comes back positive and B comes back positive and C comes back positive. Right? And so if all three tests come back positive, then the lab reports chemical X is in the sample. And so that could happen when both the sample is, chemical X is and isn't in the sample. Okay? So they could be right about that or wrong about that. And so this is equal to the probability that tests A, B, and C come back positive given that X is in the sample, plus the probability of the three tests A, B, and C coming back positive given that X is not in the sample. Okay, and so that's equal to the probability of A, this is times the probability of X plus the probability of A plus, B plus, C plus given X minus times the probability of X minus. Okay, so the reason is because this is technically the probability of all four things happening, A plus, B plus, C plus, and X plus, which is this times this. And this is the probability, the product of this is the probability of A plus, B plus, C plus, and X minus. So then this is the probability of A plus given X plus times the probability of B plus given A plus X plus the probability of C plus given A plus B plus and X plus times the probability of X plus, because this one here. So the plus here, that's it. plus this times this times this is that, and then times that. Plus, now it's a plus sign. This probability is the probability of A plus given X minus times the probability of B plus given A plus X minus times the probability of C plus given B plus A plus X minus times the probability of X minus. Okay, what is this equal to? This is equal to, this is the probability that A comes back positive given X is in the sample, that's 0.99, times the probability that B comes back positive given A came back positive and X is in the sample, that's 0.98, times the probability that C comes back positive given that A and B are positive and X is in the sample. And so that is 0.97. Times the probability that X is in the sample, which is 0.10. Plus the probability that A comes back positive given that X is not in the sample, that's 0.05. Times the probability that B comes back positive given A came back positive and X is not in the sample, that's 0.10. And times the probability that C comes back positive given A and B came back positive and X is not in the sample, and that's 0.15. And times the probability X is not in the sample, which is 0.90. And so as a decimal, that's sum of products, those four things multiplied plus those four things multiplied is equal to 0.09478. And so as a percent, if you're curious, that's 9.478%. Okay, so less than 10% chance. So 9.478. Oh, okay. So 9.478% is the percent of the samples tested that are reported to contain chemical X. Okay. And so that is the end of chapter 3. Okay. So let's keep going. Okay, so chapter 3 is done. Now chapter 4. So chapter 4 is on discrete random variables. And probability functions. So 4.1 introduction. Okay, so we're going to discuss random variables in discrete sample spaces. Okay, so we're going to discuss random variables in discrete sample spaces. That's the introduction. So 4.2 is discrete random variables. 4.2 is on discrete random variables. Okay, so a random variable, right? We discussed this briefly. So a random variable is a function that assigns a real number to each outcome of an experiment. Okay, so a random variable okay, so try to broaden your minds a little bit here, because this is going to be a little contrary to what you're used to thinking, right? You think of a variable usually as like x or y in an equation, like x plus 2y equals 5, 2x plus 1 is 3, right? You think of a variable usually in that way, an unknown or something like that, right? A random variable here is a function, so it's not like x or y with the way you normally think of it. Here, a random variable is a function. I mean, you still would have, in calculus, you still have functions, which you can think of as a variable, but okay, so a random variable is a function, and it's one whose input is an outcome of an experiment, and the output is a real number. And so a random variable takes every outcome of an experiment and spits out a real number, assigns a real number to every outcome of an experiment, right? And so that is what a random variable does. Okay? And so this picture is illustrating that idea. Okay, so if we let capital X be the random variable that is the sum of the values on two dice, then X assigns the value of 4. To the outcome 1, 3. So X of 1, 3 is equal to 4. Okay, so if we let X be the random variable that's the sum of values on two dice, then X assigns the value of 4 to the outcome 1, 3. So X of 1, 3 is equal to 4. Right? 1 is the value in the first roll of the die, 3 is the value in the second roll of the die. X of 1, 3 is a function, a random variable that takes the outcome of the experiment 1, 3 and spits out the sum of the two values, 1 plus 3, which is 4. Okay? And so in general, X of I, j, in general, if you have an outcome where the first roll of the dice is I and the second roll of the dice is j, and X is the sum of the values in the two die, then X of I, j is going to equal to I plus j, where both I and j are between 1 and 6 inclusive. Okay? So X of I, j is I plus j, where I and j are between 1 and 6 inclusive. And so that capital X is an example of a random variable. Okay. Okay, so I'm continuing 4.2 here, at the top here. If capital X is the average of 3 test scores, a random variable, then X of 60, 95, 88 is equal to 60 plus 95 plus 88 divided by 3. And so that is equal to 81. So if x is the average of 3 test scores of a random variable, then x of 60, 95, 88 equals 60 plus 95 plus 88 divided by 3, which is 81. Okay. It's just the average of those 3 test scores. You add them up, all 3 of them, and divide by 3. In general, in this case, x of I, j, k is equal to I plus j plus k divided by 3. And that's for 1 less or equal to I, j, k less or equal to 100. Okay? So in general, if x is the average of 3 test scores, which is as a random variable, then x of I, j, k is the sum I plus j plus k divided by 3, where I, j, k are range from 1 to 100 inclusive. Okay? And so that is the average of 3 test scores as a random variable. Okay, so we see 2 examples of a discrete random variable. And it's discrete because the set of input, the experiment, the sample space is discrete. Okay, so in both of these experiments, the sample space is discrete, and so because the sample space is discrete, these random variables are discrete random variables. Right? Okay. Okay. So this space is discrete because there's 36 possible simple outcomes. And so the sample space consists of 36 sample points. And so it's the sample space is a finite set. A finite set is a discrete set. So the discrete sample space. Here, the average of 3 test scores, well, the average if each test is between so it's not 1 to 100, it's 0 to 100. You can get a 0. The lowest score is not 1, it's a 0. Okay, so then if each test score is between 0 and 100 inclusive, the smallest the average could be is a 0, and the largest the average could be is 100. And so, the sample space would be each result of the test. So test 1 could be from 0 to 100, test 2 could be from 0 to 100, test 3 could be from 0 to 100. And so assuming that you're only getting integer values from 0 to 100, not any real number. So assuming that there's only finitely many choices of grade for each one, not any real number, then let's say there's 101 possibilities for each one, then the sample space would contain 101 cubed many possibilities. Okay? And so that's a finite number, and so that means the sample space is discrete. Okay? Okay, let's keep, okay, so so I'm going to stop there. And so we are now at the beginning of chapter 4. And so we've now started talking about discrete random variables. And so you see that a discrete random variable is a function that assigns to every outcome of the experiment a real number. And we'll continue talking about that soon. Okay, so tune into the next video.